Welcome to the first video for the AP Calculus AB math course.
In today's video, we will be covering the fundamentals of Chapter 1 of AP Calculus AB, such as estimating the slope of a tangent line, estimating the area under the curve, and limits. And here's Callie, the calculus cat, to join us on our journey. So first, a preview of calculus. So a derivative is how fast the rate of change is, and this rate of change could be anything from how fast water is pouring out of a pipe, or how fast somebody is pouring grains of rice into a container. This can also be called the slope of the tangent line, and you can estimate the derivative by using secant lines. So let's look at this example here. Estimate the slope of y equals x squared at the point 4, 16 using the secant lines that pass through 4, 16 and at x equals 1, 3, and 5. So if we zoom in here, we'll see that we have our points at x equals 1, x equals 3, x equals 4, and x equals 5. So if we make a secant line from x equals 1 to our point at 4, 16 here, we'll see that we get this purple line right here. But since this purple line strays from the original graph, as you can see this little blank space in between the purple line and the graph, that tells us that when we find the slope of this purple line, it's not going to be an accurate measurement of the rate of change or the derivative at the point we want to find it at, which is 4. So we're going to have to make our measurement more accurate. To do so, we can use points that are closer to the point we want to find the rate of change at, such as x equals 3 and x equals 5. And as you can see, at x equals 1 here, the slope is 5. But if we look at x equals 3 and we draw a secant line from x equals 3 to x equals 4 here, which is that blue line, we see that the slope is 7. And when we use a secant line from x equals 5 to x equals 4, which is that yellow line, we see that the slope is 9. But as you can see, the slope increases, so they're all different values here, and that just depends, and you can make the measurement more accurate by using points that are closer and closer to the point you want to find the derivative at, and using the slope of the secant line to estimate that slope, and that'll give you an accurate measurement for the derivative at that point. And so now, an antiderivative, or an integral, is essentially the area under the curve, and you can find this using left and right hand sums. So another example here, estimate the area bounded by y equals x squared plus 1 from 0 to 4 using 4 rectangles. So as you can see here, in both of these graphs, we have our function y equals x squared plus 1. And we're bounded from 0 to 4, and also here. And you can see that we've split the area under the curve into 4 separate rectangles on each side here, each with a width of 1, so this is 1, and then the height varies depending on whether it's a left-hand sum or a right-hand sum. So basically what that means is if you have a left-hand sum, what you're going to do is you're going to start at the leftmost point that you can, so for us it's 0, and you're going to connect that to the graph, so that would be f of 0 for your function, and then you're going to do this for the next point, so at 1 you're going to go to f of 1, which is here, connected to the graph, and then at 2 you're going to connect it to f of 2, which is here, and then for 3 you're going to connect it here, and then you're just going to connect these lines with horizontal lines like these, and that'll make your rectangles. So you start at the left side and move to the right, which is why it's called a left-hand sum. And when you do this for this example, you get that the area equals 16. However, if you use a right-hand sum, you're going to do essentially the same thing, but start on the right side. So you're going to connect your graph starting at the rightmost point, which is 4. So you're going to start at 4 and connect to f of 4 there, and then move to the left. Same with 3, move to the left, with 2, move to the left, and with 1, move all the way to the left. And as you can see, this gives us a different area of 31. So a good thing to remember is that a left-hand sum will always be an underestimate of the curve. As you can see, there are some gaps here, so that's why it's an underestimate of the area under the curve. But because the right-hand sum goes over the graph just a little bit like that, it'll be an overestimate of the actual area under the curve. Okay, so now let's look at finding limits graphically and numerically. So a limit is the value L that approaches a point C from the right and the left, and the actual value of f of x at point x does not matter. So this will make more sense when we look at this example here. In the graph y equals x cubed, find the limit as x approaches 1. So we said that the limit will be the value L that approaches our point, which is, in this case, x equals 1, from the right and the left. So let's use the graph to look at this. So if we come from the right side here, we see that our point, and we come to our point, we see that it's approaching y equals 1, right? And when we come from the left side of the graph to our point, we also see that it's approaching y equals 1. And so because they're approaching, both the right hand and the left hand limit are approaching the same number, we can deduce that the limit as x goes to 1 of x cubed is 1. And so there are examples of when the limit does not exist, and this is when the left-hand limit does not equal the right-hand limit. So as you can see here, the left-hand limit goes to this point, and it goes to this y value here. But the right-hand limit approaches a point up here. And since those aren't the same, we say that the limit does not exist at this point. We also say the limit does not exist when the left-hand limit or the right-hand limit go to negative infinity or infinity. So as you can see in the second example here, if we go from the left, we see that it's going to negative infinity in the x direction. And if we come from the right, we see that it's going to positive infinity in the x direction. And if these limits go to negative infinity or infinity, then the limit does not exist. And finally, if the graph of f of x oscillates too much. So in this example here, you see that it's a very wavy graph, goes up and down like this. And sometimes those waves are very close to each other, and it makes it very hard to decipher where the limit is. And so at that point, we just say that the limit does not exist because we can't find it. So you can also use a data table to find the limit instead of just relying on graphs. And so if we look at this example here, find the limit of x squared minus 5x plus 6 over x minus 3 as it approaches 3. So we have a data table here with points where our x value is approaching, so 3. But as you can see, it's D and E here. And we also have points to the left of x equals 3, so these points here. And they are relatively close to x equals 3. As you can see, they're off by just like 0.001. And then we also have points to the right of x equals 3. And these are basically our left and right hand limits. So we can look at our points to the left to see what our left hand limit is. So we see that as x approaches 3 from the left, we see that the y values are approaching 1 because it's 0.9, then 0.99, then 0.999, which is all getting closer to y equals 1. And if we look at the graph coming from the right side here, we see that our y values also approach 1. So therefore, we can say in our notation that the limit as x approaches 3 of x squared minus 5x plus 6 over x minus 3 equals 1. Now let's evaluate limits analytically. So the first method of evaluating a limit analytically is with direct substitution. So in this case here, the limit as x approaches 5 of 2x plus 3, you can just substitute x equals 5 for x in here. And so you get 2 times 5 plus 3, and that gives you the answer of 13. So that's the first way you can evaluate a limit. But if direct substitution doesn't work, you can also use other algebraic techniques, such as factoring. And so for this example, the limit as x goes to 3 of x squared minus 5x plus 6 over x minus 3, you can factor this top polynomial into x minus 3 times x minus 2, and you can see that you have a common factor in the numerator and denominator, so you can cancel those out to get the limit as x approaches 3 of x minus 2. And now you can direct substitute 3 for x here, get 3 minus 2, and your answer is 1. You can also multiply by the conjugate, and what that is basically just multiplying an expression by the opposite sign, so it'll make sense here. The limit as x approaches 7 of the square root of x plus 2 minus 3 over x minus 7. And so the conjugate here, instead of it being a negative subtraction here, it's going to be addition here. So it's like flipping the sign. So you're going to multiply it by the square root of x plus 2 plus 3 over the square root of x plus 2 plus 3. And this is equivalent to 1, and anything times 1 is just itself, which is why you can multiply, right? And so once you multiply by the conjugate, you get the limit as x approaches 7 of x plus 2 minus 9 over x minus 7 times square root of x plus 2 plus 3. And once you do direct substitution and simplifying a little bit, you get limit as x approaches 7 of x minus 7 over x minus 7 times the square root of x plus 2 plus 3. And now you can direct substitute x equals 7 here, and you will get the answer is 1/6. So there are also two special limits that you have to memorize, and that is basically just the limit as x approaches 0 of sine x over x equals 1. And the other one is the limit as x approaches 0 of 1 minus cosine x over x equals 0. So those are just two special limits you have to memorize and know. So now we have the squeeze theorem, which basically states if g of x is less than or equal to f of x, which is less than or equal to h of x for all x is not equal c in some interval about c, and the limit as x approaches c of g of x equals the limit as x approaches c of h of x equals a value L, then the limit as x approaches c of f of x will also equal L. So there's a graphical or a visual representation of what this looks like. So you have your function g of x here in orange, and that is less than or equal to f of x, which is here in black, and that is less than or equal to h of x, which is here in purple. And so as you can see, the limit as x approaches c, here this is c, for g of x, so it's this point here, equals the limit as x approaches c of h of x, which is also this point here. Then this function that is sandwiched in between the two of them, so f of x, at this point c will also have the same limit, which is L. Now let's look at continuity and one-sided limits. So there are three types of discontinuities in limits. So there's a removable discontinuity. This you can tell by basically the graph will be continuous like this, except there will be like a small discrepancy as like that hole there, where this just basically means that the y value at this point here is this black point here and not where the hole is, and that's called a removable discontinuity. And then a non-removable discontinuity is when the graph is not continuous at that point, or after to the right and the left of that point. So as you can see here, at this point there's a discontinuity here, but the graph doesn't continue in this direction, or here it doesn't continue in this direction. It's just like a jump here, which is what it's called, and that's called a non-removable discontinuity. And then the last discontinuity, again, this is also when the limit does not exist, but when the graph goes to infinity from the right or the left, and those are the types of discontinuities. And now there are 3 steps to show continuity on f of x when x equals c. So the first requirement is that f of c is defined. So there is a y value for this point x here. And the next requirement is that the limit as x goes to c or x approaches c of f of x exists. So you basically want to show that the left-hand limit and the right-hand limit are equal. And this little negative sign here and this little positive sign here just indicates that this is coming from the left and this is coming from the right. And the third requirement is that the first two steps equal each other. So that f of c equals the limit which exists. So now let's look at the IVT, or the intermediate value theorem, which states if f is continuous on the closed interval a comma b, and k is any number between f of a and f of b, then there exists at least one number c on the interval ab such that f of c equals k. So here's an example. Prove that if f of x equals 3x, f of x must equal 6 for some c value on 0 to 4. So first, for the IVT, you just have to state that the function is continuous to use it, and that's what we did here. And now you're going to find the f of x values for the endpoints of your interval, so that's 0 and 4 here. So here we have f of 0 equals 0, f of 4 equals 12. And so when we set up the inequality like this, we're saying there's a point between f of 0, which is 0, and f of 4, which is 12, and 6 is between those 2 points. And so by the IVT, you can confirm that there is a c on the interval 0 to 4 such that f of c equals 6. And so now just looking at infinite limits, just a graphed example. So here the limit as x approaches 2 from the right and the left. So if we look at it from the left here, it's approaching positive infinity in the y direction. However, if we come from the right, it's approaching negative infinity, and there's an asymptote at this point. So this is just another example of if the limits from the left and the right go to infinity, then the limit does not exist. So, in summary, we learned today how to estimate the slope of a tangent line using secant lines, how to estimate the area under the curve using left and right hand sums, and we learned a little bit about limits, proving their existence, and cases when the limit does not exist. So that's all for chapter 1. Make sure to stay tuned for the next video, recapping all of chapter 2, and we'll see you there.